what we are going to look at is how we can completely automate, not completely, but largely automate this job of classification. Okay, of course, if you have a supervised learning algorithm, you can't completely automate it because you will still have this training phase where somebody will have to manually label those typical documents falling into each of the classes with the class labels. Okay, so that part has to be done manually. But once that is done, your machine will learn how to recognize documents belonging to different classes, and from then on, you can uh, you can have it automated. And again, nobody needs to come up with patterns, right? In supervised learning, it's left to the machine to recognize patterns. You don't have to come up with a hand-coded pattern rule. And the other thing I want to mention is that in reality, you will use a mixture of classification methods. You won't use a single method. You will use a combination of some hand-coded rules, with supervised learning and so on. You could also use different kinds of supervised learning algorithms in combination with one another. So one simple um, classification algorithm that you can think of, I'm going to mention it very, very briefly here. It's called the k nearest neighbor algorithm. I'm going to mention it here because we have discussed something similar to this. If you recall cluster pruning from chapter 6, or was it 7? Chapter 7 probably, where you take a particular document. Okay, again, recall that we had mapped every document into some kind of a vector space, right? A multi-dimensional vector space. So each document became a point in that vector space, and the query itself became a point in that vector space. And then we were trying to, in cluster pruning, we defined a set of random clusters so that when a query comes, it's going to map to one of those clusters. And the way we mapped a query to a particular cluster was by looking at the nearest leader to that query. Okay, so each cluster was represented by a leader, and we computed the distance between the query, the distance in terms of the angle in that vector space, the distance between the query and each of those leaders, and we chose that particular cluster whose leader was closest to the query. So that was actually an example of what is called as a nearest neighbor algorithm, where you define the class of the query, you define which class the query falls into based on who is the nearest neighbor to the query. Now k nearest neighbors is a simple extension of that, where instead of looking at one single nearest neighbor, you look at the k nearest neighbors to you, and you do some kind of majority voting. Okay, if let's say k is 5. Okay, so you look at your 5 nearest neighbors, and let's say 3 of them belong to one class and 2 of them belong to another class. So majority of the neighbors belong to a particular class, and so you will classify this particular document or this particular query. Okay, the query itself can be thought of as a document. You'll classify this particular document into that particular class. Okay, so it's a simple extension of the nearest neighbor algorithm that we did earlier. So you have a set of documents in your training phase. Each document is labeled with a particular class, right? Now imagine putting all these documents into that vector space. Now a new document comes in. You will compute which are the k nearest neighbors to that new document. You look at what classes those k nearest neighbors fall into, and then you'll use some kind of majority voting to decide which class this new test document is going to fall into. And you can think of variants of this method, right? You can think of not just doing pure majority voting. Maybe you also want to assign some score for each of the nearest neighbors based on how maybe some neighbors are closer to your test document than other neighbors. And so you don't want each neighbor to contribute equally to the score. Maybe you want them to contribute differentially based on how close they are in terms of their real valued score to the document. right? And again, I leave it to you to think of different kinds of scoring schemes by which you can adapt this k nearest neighbor algorithm. Any questions about that? Do you see how this is a classification algorithm? Okay. So what do you want to do? Do you want to take a break or should we continue? Okay, so we'll have a 5 minutes break. Okay. Okay, so uh, we are going to begin looking at the naive Bayes algorithm for classification of documents, and this whole algorithm is going to rely on a theorem called Bayes theorem, which I hope you people have done before uh, in earlier courses, and I think Bayes theorem is also probably taught in your high school. Is that right? So the theorem just says that the probability of A intersection B is the probability of A given B multiplied by the probability of B. Usually it's written as probability of A given B is the probability of A intersection B divided by the probability of B, and likewise probability of B given A is the probability of A given B divided by the probability of A. So effectively you can write the probability of A intersection B either as probability of A given B multiplied by probability of B, or as the probability of B given A multiplied by the probability of A. Okay, and in terms of a Venn diagram, you may recall that it's it's pretty simple to understand the intuition behind this algorithm. Behind this formula. Probability of A given B is the probability that is the probability of A given that B has already happened. Okay, so let's say A and B are events. If you're given that B has already happened, that means the set of possible events are restricted to this set B. And given that, what is the probability that some event within the set A happened? So that is nothing but, so the events that are in A are in this particular area, right? If you're restricting your events just to the set B, then the events that belong to A are basically the events in this particular set. Okay, and the events and the probability of an event happening in this particular set is nothing but the size of this set divided by the total size of the set B. Okay, and the size of this set is the number of elements in A intersection B, and the size of B, the set B is the number of elements in the set B. And you can easily convert these numbers into probabilities by, because the number of elements in A intersection B divided by the number of elements in B is nothing but you divide both the numerator and denominator by the total number of elements in this particular universe. Okay, and this becomes the probability of A intersection B, this becomes the probability of B. So I hope everybody understands this formula, because this formula is really at the core of naive Bayes algorithm. If you don't understand Bayes theorem, you're not going to understand this algorithm. Any questions on that? Any questions on this particular formula? You can ignore this. Now, if you look at these two ways of expressing the probability of A intersection B, and if you equate them, you get another formula, which is also, I mean, this is just another way to express Bayes theorem. the probability of A intersection B is the probability of B intersection A multiplied by the probability of A divided by the probability of B. Okay, so this is actually the more important way in which to represent Bayes' theorem, and um, the denominator here, the probability of B, can be expressed as the probability of B given A times the probability of A plus the probability of B given the complement of A times the probability of the complement of A. Now actually this doesn't matter. It turns out that it's not going to matter, that this denominator is not going to matter for this algorithm. So if you don't understand this, uh, try to go back and look up Bayes' theorem. I'm not going to spend more time on this because it's not going to be so relevant to the algorithm. But a couple of terms that you need to know here are something called prior probability and something called a posterior probability. The prior probability uh, is the probability of, so the prior probability of an event A is the default probability with which you expect that event to happen. Okay, if you're not given any other information. Okay, so for example, what is the probability that it's going to rain tomorrow? Okay, let's say you don't know anything about what the weather today is. The probability that it's going to rain tomorrow is probably just going to be, I mean, the best estimate of that probability that you can come up with will just be the fraction of days that it has rained in the past. Right? If you have data about the last, I don't know, 100 years or so, let's say you have data about whether or not it rained in the last 100 years for every single day. You can compute what percentage of days it rained, and if you have no other information about what the weather today is, you have nothing else by which you can predict what the weather tomorrow will be, you can assign the probability that it will rain tomorrow as just the percentage of times, the percentage of days on which it has rained in the past. But let's say you're given some more information. Let's say you're given information about the weather conditions today. Then you can use that evidence. Okay, you can use some evidence that is available today to compute the probability that it's going to rain tomorrow. So that new estimated probability is called the posterior probability. So the posterior probability is the probability of an event given some evidence, and the prior probability is the probability of an event with given no evidence. Okay. These two terms will become clear in a few minutes. Uh, I just wanted to introduce those two terms, but if you didn't understand them completely, hold on for a few more minutes. So this is the formula that we're going to work with. For text classification, what we want to compute is what is the probability given a document, okay, given a document, what is the probability that the document belongs to class C, right? Recall that we had a set of classes, predefined classes, C1 to Cj, and you can think of this kind of a probability, probability of C given D, for one, you can think of a different value for each of these classes. Okay, what is the, given a document, what is the probability that it falls into class C1? What is the probability that it falls into class C2? What is the probability that it falls into class Cj? The actual class of a document is going to be the class for which this value is the highest. If we can somehow compute this particular value for every class, then the value which maximizes, then the class which maximizes this value, or the class for which the corresponding probability value is maximum, is going to be the class of this document D. Now, how do we compute probability of C given D? Well, we'll use Bayes' theorem. Okay, so we will compute the right hand side here, and I'm going to claim that the denominator doesn't matter here. Okay, so why is that? Because let's say we take the probability of the probability that the given document falls into class C1. That's the probability that's the probability of D given C1 times the probability of C divided by the probability of D. And likewise, the probability of C2 given D will be the probability of D given C2 times the probability of C2, sorry, this is C1, divided by the probability of D. Now, what really matters is which of these two is larger. Okay, we are not really concerned about the exact value, the absolute value of these two numbers. We are only concerned about what are the relative values, or which of these two is higher. Now, since the denominator is the same for both, it's better to just ignore the denominator, right? The class for which the value of the numerator is the highest is going to be the class for which the value of the whole expression is the highest, right? So it's sufficient to just maximize the numerator. Is that clear? So how do we compute this numerator? Well, this particular term P of C1 is the prior probability of class C1. That means, imagine this scenario. Okay, you're just told that, I just come and tell you that I have a new document. Can you predict which class this new document is going to fall into? Now, let's say you don't look at the contents of that document at all, without looking at the contents. Okay, so the contents of the document is the evidence based on which you will get hints about what class it belongs to. So let's say that you haven't yet seen the contents of the document. How would you predict which class it belongs to? Well, you will look at your training data. Okay, you look at your training data and you will find out which class appears most frequently in the training data. And the de facto class into which this new document will fall into is the class that appears most frequently in the training data. Right? And that is given by the prior probability of that particular class. So the prior probability of that particular class is simply the fraction of documents in the training data that are labeled with that class. Okay, so if you look at the prior probabilities here of each class, you're going to estimate them just by looking at how frequently those classes appeared in your training examples. So clearly your training data has to be large enough so as to be representative of each class. Okay, uh, if a particular class is very uncommon, then it is unlikely that a new incoming document will belong to that rare class, right? That's the intuition behind it. So looking at the prior probabilities, you can come up with some kind of an initial guess as to what class this document is going to fall into. But you also now have to rely on what evidence you're getting from the document itself. Okay, you have to peek inside the document, look at all the terms that are in the document, and see how, whether those terms give you any hint about what class it belongs to. So how do we do that? Suppose, so recall that we have a training phase where for every class we are going to be provided with a set of training examples, right? Typical examples, representative examples of documents for each of the J classes. So what we're going to do is we are going to look at the, let's say we look at 3 different documents for class C1 in the training phase. We're going to look at all the terms in these 3 documents, and we're going to record what terms appeared in these 3 documents. Similarly, we're going to record what set of terms appeared in the documents in the training data that were labeled with class C2, and so on. So look at all the terms appearing in the representative documents. Now, each document, as we have seen in the past, can be represented as a vector of terms, right? And think of this vector as just being, one, uh, each component of this vector corresponds to a particular term in the vocabulary. Okay, so what is the probability? How would you compute this particular value? What is the probability? So let's say you're given that your document is given a document from class C1. Sorry, let me put it this way. Once you see what terms appear in documents belonging to different classes, you can come up with probabilities that that these various terms appear in documents belonging to class C1, and so on. Right. So, for example, let's look at a term like medicine. What is the probability that the word medicine appears in class C1? Okay, what is the probability that medicine appears in a document belonging to class C1? Well, it's just the number of documents in C1 having that word divided by the total number of documents in C1. Right? Number of documents in C1 with that term, with having the term medicine in it, divided by the total number of documents in C1. Okay, so what is the fraction of documents in C1 in the training data for documents labeled with C1? How many of those documents, what percentage of those documents, or what fraction of those documents had the word medicine in it? That's going to be this value. Similarly, you can think of computing this value for every term in your vocabulary. Okay, maybe, so if a particular term doesn't appear in any of the documents for C1 in the training phase, then that value is going to be 0, because the numerator is going to be 0. Is that clear how we are computing the probability that a given term appears in a particular class of documents in the training phase? So forget about this. So here's what we're going to do. We are going to assume, so ultimately we have to calculate what is the probability that a particular document. So let's say you are given a test document. Okay, this is a new document that you have to classify. What is the probability that this came from class C1? Okay, that is what you have to compute on the left hand side. What is the probability, given this test document, what is the probability that it came from class C1? Now for that you have to compute the probability. So of course you have to use the prior probability of class C1, but you have to compute the probability that if I'm looking at class C1, what is the probability that I'm going to see a document D? So let's think of representing D by the set of terms that appear in it. Okay, think of this D as a vector of terms which appear in D. So let's ask yourselves this question. If I'm looking at class C1, what is the probability that I'm going to see the word W1? What is the probability that I'm going to see the word W2? What is the probability that I'm going to see this word Wn if I was looking at an arbitrary document within class C1? From those probabilities, I can compute what is the probability that I would see all these terms appear in an arbitrary document from the set from the class C1. So this is that formula again. Ultimately, this is just some notation. The class to which document D maps to is going to be the class that maximizes this particular probability value. And this particular probability value is P of C given the vector of terms that appear in that test document. And applying Bayes' theorem, we can replace this left hand side over here by the right hand side, and this is what we get. And again, because the denominator is going to be the same for all classes, we can ignore it. So the class which maximizes this value is going to be the class which maximizes just the numerator. And the numerator has two components: how likely that class is, and what is the likelihood that if I'm looking at a document in that class, I'm going to see these words x1 and x1 to xn appear in that document. And this is what we have to maximize. So that is the value of Cj for which this value is the highest will be the class of the document. Now the word naive in naive Bayes derives from this naive assumption that we're going to do. Okay, the assumption that we're going to make is that the probability of seeing words x1 to xn or x1 to x5 over here in an arbitrary document of this class C is just the product of the individual probabilities. This is not necessarily true. Okay, when do you have this kind of a condition true? When the occurrence of term x1. So if I'm given that I saw the word say Hong appear in class in a particular document, what is the what is the probability that I'm going to see the word Kong appear in that same document? Well, that's going to be relatively high because usually these two words co-occur together in documents, right? So the occurrence of Hong and Kong is not independent of one another in documents. They usually correlated, they co-occur. So if you recall from probability theory, P of A intersection B is the product of P of A and P of B when A and B are independent of one another, right? That is, this happens when P of A given B is just, so what is the probability of that what is the probability that event A occurs given that event B has occurred? It's just the probability of A. This is what it means to say that A and B are independent of one another. That is, if I tell you that B has occurred, it does not change the probability of A occurring. And that's what this is. Because if P of A given B is P of A, then you can substitute so P of A given B by Bayes' theorem is P of A intersection B divided by P of B. And if P of A given B is going to be exactly equal to P of A, okay, that means P of A intersection B is the product of these two. So whether we express independence in this way or whether we express it in this way, they are both equivalent. Okay, A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. So that's what we are assuming here, that the probability that I'm going to see x1 in a document from the class C is going to be independent of whether or not I saw x2 or x3 or x4 or x5. All these probabilities are independent of one another. This is actually not true in reality, but we are going to make this assumption because it's going to be easy for us to compute these probabilities. Okay, it's going to be hard for us to compute this particular probability. Can anyone guess why? Why are these easier to compute than computing this from your training data? I'm claiming that looking at your training data, you can easily compute what these probabilities are, but it's not so easy to compute what this is. Yeah, yeah, yeah. So similarly for other words. Similarly for other words. So and what about this? Why is this harder to compute? Hmm. Hmm. Yeah. Yeah. So in order to compute this, what do you need to do to compute this? You have to compute the among the total number of documents that are labeled with class, this particular class. How many of those documents have all five of them? How many of them have all five of these words appearing? Okay, if you're able to compute that, then you can, that gives you what the probability of these five is given C. But the problem is that you're not just going to have five different combinations. You're going to have maybe hundreds of different words, and even with five, uh, even with a if you just look at these five words to compute this, okay, how many possible combinations of five words are there? Let's say your vocabulary size is 100. So how many such probabilities will you need to pre-compute in advance to from your training phase so that you can apply them, you can store these probabilities and then use them in the test phase? Well, you'll have 5 to the power 100 possible combinations, right? Uh, okay, think about it in a different way. Clearly, your training phase has to be something that can be implemented in a reasonable amount of time, right? So maybe you will have 1,000 documents representing class C. Now, what I'm claiming is that if your training data is if it just has 1,000 documents, then it's not a large enough sample of documents for you to accurately compute what these probabilities should be, will be, because if you had say a billion documents representing class C, then you would have an enough number of them having all five of these words. But if you are just going to have 1,000 documents, you may not see all possible combinations of words appearing with a sufficiently high frequency. That's what I'm saying. Which is why this is harder. Which is why this is harder to compute, because in order to in order to accurately estimate these probabilities directly, you have to use a huge number of training examples for the class C. So the number of different the number of different probabilities that you'll have to compute, that will also be very large. That's the second problem. So there are two problems. One is that your training data is not sufficiently large that you will see this combination of 5 words occurring together in that data. And the second problem is that in reality your vocabulary size is going to be huge. So most of these values will end up becoming 0, because it's going to be very unlikely that 200 of them occurred all together in that particular document, right? Imagine this scenario. Imagine that you get a new document. So let's say this is the test document D, and let's say it's a news article on some particular event. Okay, let's say it has 1,000 words. Now if I want to compute what is the probability that all these 1,000 words will occur in a document of class C. Imagine going to looking at the training data, and do you think you will find these each of these 1,000 words occurring together in any of those documents? It's very, very unlikely, right? Unless you already have this document D itself present in your training data. But in that case, that's not good, because your test data should be different from the training data. Okay, if you just train your machine to recognize classes for a particular set of documents, and then you're going to provide the same documents in your test phase, then it's not a big deal even if your classification is accurate for documents in the training data. The real value of classification is when you can apply that particular function to new documents coming in the test phase. And if you have a new document coming in the test phase having 1,000 words, it's very unlikely that you would have seen a document in the training phase which had all of these 1,000 words. In that case, this probability will become 0 if you were to literally compute this by looking at your training data. But by splitting it like this, it's likely that each of these 1,000 words occurred somewhere or the other in the training data. And then these can be independently computed and then multiplied. And what we are saying is that the naive of the naive Bayes assumption comes uh, because of making this naive assumption that this particular probability is equal to the product of these probabilities. So we are assuming independence here, which is actually a wrong assumption, but it turns out that making this wrong assumption allows us to make the computation easier, and it actually doesn't affect the quality of classification very negatively. The quality of classification still remains relatively high. Now, why do you think that is the case? Because if these two are not, if the left hand side is usually not equal to the right hand side, then don't you expect something wrong, something to get bungled up? And that brings us back to this particular point I made here, that it doesn't matter if you're not able to compute the value of this probability accurately. What matters is that it should be accurate enough that the relative values, the relative comparisons between these probabilities remain preserved. Okay, ultimately what you're concerned with are the relative values of these probabilities. It doesn't matter if you're not able to estimate the absolute values that accurately. So making this assumption does lead to inaccuracies in the absolute value, but it turns out that if you look at the relative values, those are generally not affected. Okay, and there's no, I'm not giving you a formal proof of that. I'm just saying that in practice, this is what you observe, which is why naive Bayes tends to be used in practice. Any questions about this algorithm? Let me see if there's. Uh, Let me summarize the algorithm again. We are going to. So in the training phase of the algorithm, for each class Cj, okay, compute the prior probabilities for all those j classes. And what will be the prior probabilities? They will just be the fraction of documents among the total number of documents in the training phase which are labeled with that class. Okay, so this should be simple. The other thing you have to compute is for every term in the vocabulary. Okay, compute Cj, and for every term in the vocabulary, okay, let's say the ith term in the vocabulary is x sub I, you have to compute the probability that you will see this word in an arbitrary document of this class. And how will you compute this from the training data? Well, you look at the total number of documents that belong to class Cj, and you see how many of them have this particular vocabulary term x sub I appearing in it. Okay, so in the numerator you have all the documents belonging to the class Cj which also have the term x sub I appearing in it, and in the denominator you have the total number of documents belonging to class Cj. Okay, so here you're just computing here the fraction of documents in the class Cj which have this particular term. So in some ways this is like the document frequency, right? If you go back to the earlier lectures, the document frequency of a particular word or of a particular term was the total number of documents in the corpus which have that term, right? Now if you just convert it into a fraction, okay, the document frequency there was an integer value. Here we are just think of converting it into a fraction where you're also dividing it by the total number of documents in the corpus. Okay, so this is analogous to that. Of course, here you're not dividing by the total number of documents in the corpus. Here you're dividing by the total number of documents belonging to labeled with class Cj in your training data, and in the numerator you have among all these documents how many of them have this particular term appearing in them. So if you compute these set of probabilities, okay, one for each class, and how many values of probabilities will be there for how many such probabilities will be there? The size of your vocabulary multiplied by the total number of classes you have. Okay, because for each class you will be computing these probabilities for every term in the vocabulary. So you'll have these many values of probability to compute in your training phase for this particular expression, and of course plus j more values coming from the prior probabilities. And then you will use um, Bayes theorem. Okay, so let's say a document D comes which has um, terms x1, x2 and so on till xm. Okay, so let's say we represent a test document by this vector. We're going to compute the probability that this document belongs to each of the classes. Okay, so what is the probability that the document belongs to class C1? Okay, what is the probability of what is the probability that the class is C1 given this document. That will simply be the probability of seeing terms x1 to xm appear in an arbitrary document of class C1 multiplied by the prior probability of class C1 divided by the probability of this document. And as I said, because this value is going to be the same for all the classes, we can just ignore it, because ultimately we want to choose the class which maximizes this numerator. Now this value you would know because you would have computed these prior probabilities. And for computing this value, probability of x1 to xm given C1, you will use that naive assumption to say that this is equal to probability of x1 given C times the probability of x2 given C, and so on, where each of these values can be looked up because you would have computed them in the training phase. So you'll compute the numerator here for all the classes, and you will find out for which class was this value the highest, and that is the classification for that particular document. So this is a summary of the algorithm. Any questions on this? Mm-hmm. Oh, so you're asking why we can make this naive assumption without things getting screwed up? Yeah, so what I said was, if you were actually interested in estimating the value of P of C1 given D, then the value that you would get by making this naive assumption will be inaccurate, because this assumption is generally not true, as we saw for the word Hong Kong. But we are not concerned here about the values of the actual value of P of C1 given D. We are only interested in the relative order of the values of P of C1 given D, P of C2 given D. We just want to find out which of these different values is the highest. Okay, this one, is it this one, is it this one, is it this one? Now each of these values are going to be biased because of each of these values is going to be inaccurate because of this naive assumption. But it turns out that the inaccuracies are sort of similar in all of them, so that their relative values don't change. Okay, so for example, if I want to compute which of x and y is the largest, and let's say I don't have the value of x, I have the value of x by 10 and I have the value of y by 10, it's sufficient to compute which of these two is the larger, and based on that I know which of these two is the larger. Of course, this is a very simple example. You know that if x by 10 is larger than y by 10, then x must be larger than y. Whereas here, there's no easy way to prove that the ordering will be preserved. Okay, I can't mathematically prove that. In fact, theoretically, it's possible that the ordering could get screwed up here. But in practice, that doesn't happen. In practice, naive Bayes can afford to be inaccurate without the classification itself being inaccurate. So the estimation of these values is inaccurate, but the end classification is not going to be so inaccurate. It's going to be relatively accurate. That's what I said. Is that clear now? Okay, so one of the things I want to point out here is, in real life, it is possible for you to get a test document having a word that you have never seen before. if such a scenario happens, what will be the probability that you will end up computing? Any guesses? Let's say you have a test document which has a word that you have never seen before. Yeah, yeah. The probability will become zero because if you just if you look at, so let's say that new word was, I don't know, arachnocentric maybe. Okay, so what is the probability that the word arachnocentric appears in a document of class C? That's going to be zero because there were no documents having that word in your training data. So the right hand side will become totally zero just because one of the words was a word that you hadn't seen before. Now that's not actually good because just one new word can end up destroying your classification scheme altogether. In reality, you have to allow for your test documents to have words that you have not seen in your training phase. And even if you've seen that word in the training phase, maybe you didn't see it in the documents for class C1. Okay, maybe the word arachnocentric was somewhere in the training phase, but maybe it was there in a document belonging to some other class. That doesn't mean that arachnocentric can never appear in a document of class C1. Okay, all that implies is maybe it doesn't appear as commonly in class C1 as we thought, because if we had a sufficient number of examples from class C1 and if that word didn't appear in them, that means it's a relatively rare word, which is not to say that it's impossible for it to appear in class C1. Okay, we don't want that to happen. So what we do is we use something called smoothing to allow for such outliers. Okay, we want to theoretically permit new words to be in the test documents without destroying the classification scheme. So what we do is imagine the following scenario. Imagine that every class, imagine that in the training phase, each of these classes not only has terms corresponding, not only has terms that are contained in the documents labeled with that class, but it also has every term in the vocabulary appearing once. Okay, so if the vocabulary has 100,000 words, I'm going to assume that the training data for C1 not only consisted of the documents that were presented to it, but it also consisted of one occurrence of all of these 100,000 words in the training data itself. And I'm going to do this for every class. And this is just to allow every word to be theoretically permissible for every class. Okay, so if that happens, then uh, you can you can see that you'll never get a value of 0 for any word. Okay, you'll get a very small value, of course, but it's not going to be 0. Okay, you'll get a very small value for words that did not appear in the documents, but it's not going to be 0 because every word occurs at least once in every class using this kind of a smoothing scheme. And there are different ways to do smoothing. Okay, this is the simplest possible way. This is a way you can understand intuitively. Do you understand the purpose for doing smoothing? That is what we are imposing from our side in by doing this kind of smoothing, because if you don't do that, then you're going to get a probability of 0. You don't want a probability of 1, by the way. I think you were saying earlier that maybe you can make it 1. You don't want to make it 1 because in that case, a document which doesn't have that word will definitely not belong to that class, right? Because then you're necessitating that every document in that class must contain that word. Of course, if it was a totally brand new word not appearing in any of the classes, then you could do that because then all of them would get affected in the same way. But in reality, you would do some kind of smoothing to allow these probabilities to be non-zero. Okay, so here's an example. What if we have seen no training documents with the word muscle ache appearing in the class flu? In that case, the probability of muscle ache given the class flu would be 0. And that would make the entire value 0, which is not good, and so we try to do smoothing. Okay, I think we're out of time. So, do you have any final questions before we end?